Hey everyone, welcome to the discussion on dark energy. So just an overview, just first of all, and a brief review of some of the material from dark matter and how is dark matter different from dark energy. Many people can get them confused, and ultimately both of these are really inadequate names for what the stuff actually is. But what is it, and how did we measure it? What alternatives might exist to it, and how does this lead into the cosmological constant? And in particular, there's a cosmological constant problem that will be the topic of the next lecture. But first of all, a review of dark matter. It's not dark. It's transparent. It doesn't interact with light at all. Here's an example of actual dark matter on the right. It's dark and made of matter, but it's not dark matter. So that's the first thing, but matter is just not a way to say stuff. What matter means in physics is that its energy density dilutes with inverse volume. I'll show an example of that on a few slides, and this is different from how, say, radiation dilutes. It dilutes faster than inverse volume, and so there's a difference between the two. And the main evidences for dark matter, of course, there were the cluster rotation physics, the galaxy rotation curves, large-scale galactic structure, gravitational lensing, and the cosmic microwave background. So here is an overview of dark energy. Dark energy is also transparent. But it's even more misleading than the dark matter name because dark energy isn't even actually energy, it's an energy density. So it's like a transparent energy density, which is very different from the phrase dark energy. But it sounds cool and mysterious and so on and so forth. But it's really not that mysterious. And it was something that was proposed and put into the equations of general relativity, at least the simplest form of dark energy, which is whenever its energy density remains constant with the increase of volume. And if it's constant, then it's called the cosmological constant, which is what Einstein added to his equations to get the universe from collapsing upon itself. And what are some of the main evidences, and how did we end up with a Nobel Prize being awarded for the discovery of this dark energy density? Well, come to that. But first, we need to pay a little bit of attention to how different types of matter change as the universe expands, in particular with their densities. So here is an example of how matter dilutes as the universe expands. Basically, the amount of matter in the universe doesn't change over time, but its density would. So you can imagine if you had 10 particles, and then all of a sudden your overall volume gets bigger and bigger and bigger, the density of matter would go ahead and decrease. But then, here's an example of radiation. Radiation would do the same thing. Here's an example of 3 photons, and then you have those 3 photons spread out over a farther space. But it turns out that radiation has an additional term where the wavelength of the photons are actually getting stretched as well. And so instead of decreasing with inverse volume, it decreases with the inverse radius to the 4th power instead of to the 3rd power. But then here's the idea of dark energy. And so what does that do over time? Well, the overall density of this, if it's a cosmological constant, is just constant. So that means that the universe expands, the overall energy density doesn't dilute. And the thing we're going to look at next is what impact does the density of matter, does the density of radiation, and does the density of dark energy have on the expansion rate of the universe? And here is on the right side, or the middle of this particular slide, is how the expansion rate is impacted by the decreasing density of matter. And you see the expansion rate is influenced a lot by it at first, but it gradually decays. And then the influence of radiation, similar. But the interesting thing is that what effect does the cosmological constant have on the expansion rate? And it would be constant. But really, to understand why that's the case, we need to come back to the Friedmann equation. In particular, you could rewrite the Friedmann equation like this. So on the left-hand side, you have the Hubble parameter, which is basically related to how fast the region between 2 points in space is changing as a function of the size of the universe. And that's divided by a constant, which is h naught, the Hubble constant. And on the right-hand side, well, four different terms here. First of all, there's the fractional energy density of radiation, and the impact of that on the expansion rate, or the Hubble parameter, decreases as the scale factor to the fourth power. I just wrote radius, but really it's the scale factor. You can, of course, get the radius from the scale factor, but it's usually just described in regards to the scale factor. And then there's, of course, the fractional energy density of matter. And how is that going to affect the Hubble parameter, or how fast the universe is going to be expanding? Well, it just so happens that it will have a pretty good impact early on, but then it will decrease as the universe gets bigger and bigger and bigger, because the overall density of matter is also decreasing. The next term we're going to look at, that's an important term, which is one of the reasons why some cosmologists proposed, even before we had discovered evidence for dark energy, is that the overall curvature of the universe is something that's very interesting. So we'll come back to that. But then, of course, the last term would be the fractional energy density of dark energy, which is just constant. So the impact that that has on the expansion rate of the universe would be constant. So a simple question that I'll just read and that you could either pause the video or just follow along is, which terms would be the most important when the universe is much smaller? And the universe is much smaller when the scale factor is smaller. So in particular, the little term a at present is equal to 1, and in the past, a would have been much, 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 much smaller. But then which terms become more important as the universe gets bigger? And then which terms are going to dominate in the future? Well, here's an example of that. In the early universe, which terms would have been most important? Well, it would have been the fractional energy density of radiation and the fractional energy density of matter. Because if you're dividing by a much, much smaller scale factor, then those terms are going to dominate the overall expansion rate of the early universe. And here's just a plot of the energy density as a function of redshift. So z equals 0 is at present, and going back into the past, those are different eras in time. And then, of course, the curvature of the universe will become increasingly important as the universe gets bigger. But in the future, and even at present, it turns out that as the universe gets bigger and bigger and bigger, the relative impact of the fractional energy density of radiation and matter and the curvature are going to become negligible, because the only term that doesn't decay is the fractional energy density of dark energy. So let's look a little bit more at the curvature. This is a pretty interesting term in particular. This term here, this is omega k, this is the fractional energy density of the curvature of the universe. And what is the curvature of the universe? Well, again, it would be, typically this could be thought of as one of three main geometries. One would be a flat geometry or Euclidean geometry. You can have a closed or curved one, or an open and hyperbolic one. In the top left, there's a brief example of what space-time itself looks like. So if you see that there's the saddle, that's the left image, then there's the flat one in the middle, and then there's the curved one on the right. Now we know that geometry works quite a bit different depending on what your surface looks like. So for example, to travel on a straight line on the Earth, if you ride on an airplane, you are not actually traveling in a straight line. You're traveling on a geodesic. You are traveling on the shortest path, and unless, of course, you have to loop around because of weather conditions or something. I'm kidding, but you would travel on a curved path even whenever you drive in your car, airplane, so on and so forth. And that could be true about our universe as a whole. There should be no reason as to why necessarily it has to be any one of these particular geometries. But it turns out that the type of geometry would have some really important impacts on how wide the spacing of the anisotropies would be in the cosmic microwave background. And so measurements of that, turns out that we can measure the overall fractional energy density of the curvature to be almost entirely flat, at least at present. And that leads into the so-called flatness problem that we'll talk about whenever we get to inflation. But it's an interesting result. So if the universe is flat, what does that mean for the other stuff? in there? Well, basically, it means that the fractional energy density of the other stuff has to add up to 1. It doesn't really have to be flat, and this this kind of hints upon a little bit of a bias, or not bias, but just a funny thing about the physicists like. We kind of like for things to equal 0 or 1, and we don't like for them to be really big or really small. And really what that comes down to is asking the question of what is natural versus unnatural. But even then, natural versus unnatural have very specific meanings that we'll come back to when we talk about fine-tuning and inflation in a future lecture. But if you want to add up the overall energy density of radiation, it's really small. This term would only have an impact in the very earliest moments of the universe. And then how about matter? Well, it's quite a bit larger, but it's still a long ways from 1. And of course, the fractional energy density of matter includes all kinds of matter, including dark matter, which we have a very good measurement on how much of that actually exists. And then there's also, so what does that leave that's left? Well, that just leaves that the remainder, 1 minus the fractional energy density of matter, is how much the energy density of dark energy is, excuse me, not dark matter, dark energy. But how would one actually measure this? I mean, this is great and all, and this is just a calculation that one could do, but it turns out that there were some expectations that we had. Well, actually, we expected the opposite, because at one point not so long ago, we generally didn't write any kind of dark energy or cosmological constant in the equations of general relativity or the Friedmann equations, because we had no evidence that the term actually existed. We were able to describe, there were a few anomalies that we'll come back to, but basically we were able to describe most of the universe without it. And so it's really interesting. What do these equations predict? Well, these two terms, if you only have the radiation and matter terms, they predict that the rate of expansion, or the Hubble parameter, should be decreasing over time, or decreasing as the universe gets bigger. So we were looking for evidence that the universe was decelerating. But you can see these animals here, we basically found the opposite. But first of all, how did we plan to do that? Well, here is an example of one of the things that helped us to even begin to try to make this measurement. This is the return of the standard candle. Of course, here's an example of candles at many different distances in space, and if they all have the same brightness, you could just simply measure how bright it appears to be and then calculate how far away it is. Pretty simple idea. And so Cepheid variable stars, that was something that we had discussed previously, and they're great, but they really only work out until maybe the Andromeda galaxy. But that's it. That's only a few million light years away. This is not billions of light years away. And so it turns out that to get such an object, you would need something that is really, really, really bright. In particular, something like that. So here is an interesting type of curve that you get, a very characteristic type of curve, and this is coming from supernova eruption, in particular type 1a supernova eruption. The peak is so bright, it's comparable to a single galaxy, and there is a relation between how bright it is and the rate of decline. Typically, those that are brighter decline just a little bit slower than those that are less bright. So basically what this means is that these are standardizable candles, and you could just simply compare. You can calculate the distance from this, you can measure the redshift, and compare the two and find something very, very interesting about that. That all of a sudden, whenever you compare the two, it doesn't match up with what we were expecting. In particular, there are deviations from this curve. So there's a few things here. On the left-hand side, here's an example of a best fit of the current data with an accelerating universe. What we were expecting was the red curve there. That would be a decelerating universe where the amount of stuff was at the critical density. And for an empty universe, there you have there in the middle. And so yeah, we have a lot of confidence that indeed that this was some of the first evidence of an accelerating universe. And you might have another example there where you can go ahead. Excuse me. So you have three curves there, and the first one is whenever the energy density of matter is at about 0.3 of the critical density, and the energy density of dark energy is at 0.7 of the critical density. And then you have the black curve there. And then you have the curve in red. And the curve in red is if the universe is only made up of matter. There's no dark energy at all, and the universe is flat. So the problem is that you need these numbers to add up to 1. So the black curve actually works kind of well if you look closely enough. But the problem is that we know the universe is pretty flat. So the sum of the fractional energy density of matter plus the fractional energy density of dark energy has to add up to 1. So even though the black curve can work, it's constrained heavily by measurements of the flatness. So basically you're comparing, in this particular example, the blue curve and the red curve. And you see that the data agrees a lot more with an accelerating universe that has a significant total fraction of the fractional energy density of presence made up of dark energy. Here's another example. But again, just kind of recapping how the Friedmann equation tells us these things is that the Friedmann equations tell us how the universe will evolve given the stuff inside of it. So if there was only, this is a really important result, if it was just matter, radiation, and curvature, it should decelerate as the universe expands. But it turns out that in our universe, what we see is that, well, if you have matter, radiation, and curvature, it will decelerate until the term involving the cosmological constant gets bigger than those three. And if you recall going back several slides, I put up an example of how the different energy densities decrease as the universe gets bigger. And eventually you see there's a point where the fractional energy density of dark energy takes over the other ones. And so that is the only one that's really consistent, where the universe decelerated in the past because the radiation and matter terms were more important, but now it's accelerating because the dark energy term dominates. Here's an example of comparing some different models of the universe, similar to the one a few slides back. So if you look at the top left one here, this is looking at three possibilities. This is that the universe is made up of just a whole bunch of dark energy. That's the blue line on the bottom. Or it's solely made up of matter. Or there's a mixture of matter and dark energy. And you see that the one that's a mixture of about 30% matter and about 70% dark energy is the one that matches the data the best. That's coming from measurements of various supernova eruptions, so on and so forth. If you look at things like baryonic acoustic oscillations that we'll come back to when we discuss inflation, you see that that one agrees really, really well with the model that has about 30% and 70%. Another interesting thing is that the universe without dark energy would actually be about 9 billion years old. Here's an example of that here, where you have the age today, and the universe would only be 9 billion years old if there was no such thing as dark energy. But with an amount of dark energy, you find that the universe turns out to be closer to 14 billion years old. So basically, why was this a problem, or why is this interesting? Well, this is really interesting because we were getting measurements of stuff that was older than the universe was itself. That would be a problem. But first, that requires looking at some HR diagrams, Hertzsprung-Russell diagrams. And so this is a really interesting diagram that there's a lot going on in this. I'll unpack a little bit of this diagram. here, but you see there's this band in the middle that's fairly diagonal. It's called the main sequence band. And then there's this area labeled as giants and then supergiants. Then you see in connecting those in the main sequence, there's what's called the instability strip. And then you see white dwarfs down here in the bottom left of the graph. And so this graph is interesting. If you look at the top, it goes from a lower temperature to a higher temperature. And if you look at the right, this is luminosity compared to the sun. So it goes to something that's much more dim on the bottom to the top. I wouldn't really look at the left axis. It's kind of a funny way that it's done. And the bottom one as well, spectral class. That's a useful way for talking about stars really quickly because it's easier just to talk about a spectral class instead of having to remember, oh, 7,000 Kelvin, 10,000 Kelvin, 6,000 Kelvin, 4,000, and so on and so forth. So it's much easier to talk about spectral class if you're going to be talking about a lot of stars. So the majority of stars in our galaxy are found in the main sequence. And so they tend to get hotter and hotter, and eventually they leave the main sequence when they die. And I'll show you some examples of what happens whenever that occurs. And again, those are the common regions that I looked at. So if you want to look at M-class stars, how should we look at these stars in particular? You see a few. You see some down in the bottom right. There's Barnard's star, and then in Proxima Centauri, and then you have and they have a particular temperature. But if you follow up that band going up higher, they have the same temperature, but they're much, much brighter. How could it be that two stars have the same temperature, but one's much brighter? Well, it turns out that you can have the same temperature, but the total luminosity of a star, you see there's a little equation there that it's equal to the radius squared times the temperature to the fourth power times Boltzmann's constant times 4 pi. But you can see here is that if you have the same temperature, you can get stars that are much, much more bright if they're bigger. And so what does that tell us? That's why these are labeled as giants and supergiants, because they have the same temperature as main sequence stars, but they're much, much bigger. So that's just a way to look at the diagram. There's a lot of ways to look at that. The main sequence stars, though, are some of the most interesting stars in the entire diagram. Well, they all are. But the stars in the main sequence, they're in what's called hydrostatic equilibrium. Basically, there's this inward pressure of gravity aiming to crush the stars together, but there's an outward pressure of gas, and it's balanced. And these stars are in comfortable equilibrium until they run out of fuel. And there's a nice relationship that we have between the mass and the luminosity. So that's going to be important in terms of calculating the lifespan of these stars. It's pretty simple. There's a little thing I wrote at the bottom. The lifespan is pretty simple. It's just the rate of burning fuel, which would be related to its luminosity, compared to the amount of fuel, which is its mass. And so if you go back, you can see the mass and luminosity relationship. And from there, you can really just calculate the lifespan of different stars. So if you have, for example, a star that has the mass of our sun, it has a lifespan of about 10 billion years. If you have one that's close to 60 solar masses, it has a lifespan of not 10 billion years, not a billion years, but just 3 million years. And if you have, though, a star that's much, much smaller, well, it turns out it can have a lifespan not of just 10 billion years, but 2,000 billion years or 2 trillion years, which is really quite remarkable. And so here's an interesting thing. Whenever you have a new cluster forming, you'll have a perfect example. An HR diagram would look something like this. If you were able to measure a cluster that just formed, you would have a wide array of different stars. Some would be bigger, some would be smaller, and as a result, but they would all be forming at the same time and in hydrostatic equilibrium. And so you get a diagram that would look something like this. And the question is, what happens to this cluster as it ages? Well, which stars are going to be the first to die? Well, it would be those that have a much, much heavier mass, or those that are much brighter. In this particular case, they'd be those in the top left. So your diagram should start to look like this as it ages. So here's an example of the same cluster modeled at 50 or 10 million years of age. And you find that those stars, the stars that were on the main sequence, have since died. And they've either entered into some kind of giant or supergiant phase, and how they evolve, leaving the main sequence, is really interesting and beyond the scope of what we'll cover now. I would encourage you to look that up if you're curious. It's really cool. But essentially, this is what happened. One by one, stars would start leaving the main sequence. Here's an example of that, where you have a particular cluster and you see stars leaving the main sequence, and little by little. And so it's going to repeat if you watch it here in a second. And you see it takes longer and longer to leave the main sequence, but the first stars tend to leave fairly quickly. And then eventually that one represents a star that has a mass of our sun, and it eventually explodes, and then many of them enter down into the bottom left of the particular diagram. Some of the heaviest ones become black holes and other more exotic structures. But eventually you would have many different types of white dwarfs forming, and that's where you see that band there in the bottom left. And that also tells us something interesting about our universe. So this is pretty cool that you can go ahead and compare this and ask, how old is a galaxy cluster? Well, here's a measurement of the observed Pleiades cluster. If you go ahead and plot this on an HR diagram, you can calculate and model how old the Pleiades star cluster is. How long ago did this Pleiades star cluster form? Well, we know from the turnoff point from the main sequence, it's about 50 million years old. And the stars that were much bigger, they've all since died. They've all since left the main sequence. But there hasn't been enough time for stars, many of the stars, to leave the main sequence. And so you might find some kind of graph like this. Here's a diagram for globular cluster M13. So here you see the main sequence, and many stars have left the main sequence. You see a pretty clear marked turn-off point. You see this instability zone. You see some red giants, and then you see a horizontal branch that are in the post-red giant branch. And where are those stars going? Some of them are going to the white dwarf section that you saw in that simulation a few slides ago. It's really interesting. And one of the simplest ways, and this is a crude way to go ahead and figure out how old a cluster is to just simply ask, well, where's the turnoff point? What stars haven't died yet? And it's a pretty simple thing that you could do. And this cluster is at least 11.5 billion years old. Now, you put this type of thing into the context of the age of the universe, that before we knew of this cosmological constant, well, it turns out from the Friedmann equations, you got a universe that was 9 billion years old. And then we're looking at globular clusters, and it appears that globular clusters are at least 11.5 billion years old. So you can't have a globular cluster be older than your universe. And here's an example of a distribution of many different clusters. The lower bound was about 10.4 billion years with 95% confidence. And then the median, or I think the mean or best fit age, was around 12.6 billion years old. And this is looking at many different globular clusters. Interestingly enough, that's really similar to nuclear chronometry, which would be comparing different radioisotope ratios of different elements. So you could look at thorium or uranium, lead, so on and so forth. And those found a very similar result as where it gave a firm lower bound of 9.5 billion years. So the universe is at least 9.5 billion years old, but it had a best fit age of being 12.8 billion years old. So basically, when you get these best fit ages, that tells you that on average, these would tell you, if you take the average of them, that the universe is at least this old. And interestingly enough, we also can measure the oldest white dwarfs and find that they are also on the order of at least 11 billion years old. And the oldest stars to radiometrically date directly, which is a star that had, I think, 6 different radioisotopes in it. And we got a really nice measurement of that. And the oldest star that we could date directly dates to being over 13 billion years old. And so this is a really important result, that we're measuring the ages of all of these things, and at one point they were older than the universe itself. But it turns out that with the advent of the discovery of this energy density to space, it turns out that the universe, we can calculate its age really well. So it's pretty simple. If you have the Friedman equations, if you know how much stuff is in the universe, you can just calculate it. There's a little formula there to calculate the particular age as a function of the scale factor. And so it would be a scale factor of 1 at present, and you could go ahead and do that with the different fractional energy densities and the Hubble, parameter is in there. And here's an example of how we can constrain the amount of dark energy by a large number of different ways. So this is how it's typically done. Because we know the universe is flat, let's look at that one first. That's a flat line, it's horizontal. And we know that the sum of the x-axis, which is the fractional energy density of matter, and the y-axis, which is the fractional energy density of, well, dark energy, the sum of the two has to equal 1. So you see here that because we know the universe is flat, the solution to how much dark energy exists and how much matter exists has to lie on that line. And then you could take the data from the supernova eruptions, and that's the one in blue, and you could go ahead and constrain that. And then you would be able to compare the two. So you would say that, well, this is where I have with 95% confident with supernova eruptions. And then, because I know the universe is flat, I can constrain that even tighter. And the cosmic microwave background has provided some nice constraints for matter and dark energy. And then the baryonic acoustic oscillations have been really, really key in refining the overall fractional energy density of matter in particular. And so when you combine all of these, you get a really, really nice measurement for what is the fractional energy density of matter and the fractional energy density of dark energy. And as we're able to measure these more and more precisely, we're able to get a much, much tighter constraint on what the actual universe is made up of. And as we do that, we can measure and calculate with more precision things like the age of the universe. So this is a really precise thing where you can go ahead and measure based upon the error bars that the age of the universe is 13.801 plus or minus 0.024 billion years old. And then, of course, there's the obligatory shout out to the steady state model, which I think is what's represented up there on the top left. If that's not the case, you can correct me, but the steady state model still makes it onto these, and you see that the data just doesn't align with it. Now, of course, an interesting question is what would our universe be like without dark energy? Do we really need it? Um, well, I don't know. I mean, maybe it wouldn't have been too different, at least in these kinds of ways. The Hubble constant would be a little different. The cosmic microwave background a little cooler. We'd eventually be able to reach every galaxy. The Hubble rate would eventually drop to 0. And yeah, I mean, you really would have superclusters existing. That's an interesting thing about with dark energy that we'll come back to and reflect on a little bit, where if you really have an accelerating expansion of the universe, even though we see these big structures, they're not going to be gravitationally bound in the future. They're essentially going to be ripped apart without ever being able to form these superclusters. But of course, none of these really describe our real universe. And the cool thing about the real universe is that it didn't conform to our expectations. We thought there was no dark energy because we had no evidence of such. And the flatness of the universe started to clue us into maybe that there was something, but we were looking for the opposite. And we were looking for evidence that the universe was decelerating in its expansion. But we found the opposite, and two groups won Nobel Prize. And it turns out here is a measurement well, here's a plot of two different points. So at one point I mentioned that dark energy would take over, and this is whenever the expansion rate of the universe would stop decelerating and start accelerating. And so the universe has been accelerating for a little bit of time, but if you interpolate this into the future, essentially the distance between points is just going to keep getting farther and farther and farther apart. Essentially, our universe, it's kind of a depressing end, I guess, in some sense, of a universe with a true cosmological constant. The universe is just going to accelerate and all lead to the so-called heat death of the universe. Um, where all consciousness will cease because all processes based upon thermodynamics won't be able to take place. And so it's just going to be a rather grim future for our universe if this is indeed the case. And this is pretty cool. Here is an example of actual measurements of this expansion history of the universe. And there's the look back time. The red data point there is from the BOSS collaboration in terms of measuring some quasar data at high redshifts, finding that the universe was accelerating faster in the past, but we have measurements of it decelerating and now accelerating. And this is a really, really cool thing that we've actually measured the universe decelerating and accelerating. That lets us know that we have a very, very good idea of what makes up the overall energy density of the entire universe, and that the Friedmann equations give us a good idea of what the universe is, and that we know very, very precisely how old our universe is, 13.8 billion years old. And so that's a lot we have a lot of confidence in those types of measurements. But what is dark energy? That is a great question. The simplest answer that we'll get into when we talk about the cosmological constant problem is just it's a property of space itself. It's not really that surprising. It's something that was written down in the equations, and its energy density is really, really small. It's about 5 protons per cubic meter at present, and that's really nothing. That's so little if you try to imagine a cubic meter and there's only 5 protons in this, which is nothing. You would never be able to notice dark energy, but when you add that up, that little amount over large scales, it starts to significantly change how the universe behaves on big scales. And perhaps it's better thought of as a smooth tension. So instead of dark energy, let's call it a smooth tension. But of course, dark energy is the cool name. And again, it's really a transparent energy density. And a few things is that if it really is constant, it's called the cosmological constant. But we don't know if it's constant yet. Here's an example diagram of, instead of having the fractional energy density of the cosmological constant, or dark energy, plotted on the y-axis, this time it's what's called the dark energy equation of state. And on the x-axis is still the overall fractional energy density of matter. And so the equation of state is really interesting. And if it's equal to -1, exactly, then that means that the dark energy is the cosmological constant. It's constant. But it turns out that there are a lot of data points that can be consistent with the equation of state, or W, being less than -1. Or it could still be consistent with -1, or it could be greater than -1. And so there are some really, really interesting possibilities that lie out there that let us know that maybe dark energy is something that's quite a bit more complicated. The cosmological constant is the simplest explanation of what dark energy is. It's just a property of space itself. It's just an energy density of space. It's really small, and it's not really that surprising. It's a natural thing that Einstein added to his equations a long time ago, and we took it out because we didn't need it, but now we need it again with more precise measurements of the universe. But yeah, if it's a little bit bigger or smaller than -1, then that means that dark energy is something quite a bit more exotic, which I think is really exciting. It would be really exciting. I'm personally hoping that it is greater than -1, but who knows? Better measurements will hopefully be able to refine that. So paying attention to these measurements with the dark energy equation of state, I think, will be really exciting for letting us know what dark energy is. And so that's just a little overview of dark energy. I hope you liked it, and the next one to come will be the cosmological constant and the cosmological constant problem.